In these slides, we want to see how to get a relationship between the induced charge and the charge on the conductors, sigma. So let's review what we discussed before. If you put the insulating material inside the capacitor between the two conducting plates, we said that there's going to be some negative charge sticking out on the left, called the induced charge, and some positive charge sticking out on the right, also induced charge. This is sigma, this is minus sigma induced and minus sigma induced. And the charge on the conductors is plus sigma and minus sigma. And there are two ways we can write down the fact that the electric field is weaker inside the material. E node points to the right, E induced points to the left. So the total electric field is E node minus E induced. This is just the superposition principle, and it's very easy to see how we can write down the total electric field this way. But we can also write down the total electric field inside after the dielectric is inserted. We can write it as E node divided by a factor of K, and the factor of K is something bigger than 1. So this also shows that the electric field is getting weaker. Now, why would we write down the electric field this way? Because the factor K is something very easy to measure in the lab. You can actually find in any textbook a list of each material and the factor K for that material. For instance, paper is 3.7 and Pyrex is 5.6, and so on. It's very easy to measure this factor of K. You can measure the potential difference before and after, and the ratio will give you the factor of K. So what is the electric field due to the two parallel plates with charge density sigma? If you take this conducting plate that has charge sigma, remember these are sheets. We're just looking at the cross section, but this is a sheet that's coming out of the page. And this conductor with charge minus sigma, these two sheets only. What's the electric field E node due to those two sheets? Well, we've taken before, when we used in the chapter on Gauss's law, we found the electric field due to one sheet, and then we found the electric field when you have two sheets with opposite sign, and we found the electric field inside in the region between them. So if you can't remember this, go back to those videos and see that. We found that the electric field is just sigma over epsilon naught. Okay, what is the electric field due to the sigma induced sheet and the minus sigma induced sheet? Well, it's the same formula. It's the electric field is sigma induced over epsilon naught. So if we look at now that formula that we had for the total electric field, and we wrote it two ways. One way is that it's E node over a factor K, and the other way we wrote with the superposition principle, it's E node minus E induced. Now we know that E node is sigma over epsilon naught. We know that E induced is sigma induced over epsilon naught. We can just substitute E node into here and substitute E induced into here. And that will then give us a relationship between sigma and sigma induced. So we just need to simplify this. The epsilon nodes will all cancel out, and we can rearrange the terms a little bit. And when you rearrange and you get sigma induced on one side, and take a common factor here with sigma, you get that sigma induced is sigma times 1 minus 1 over K. Since K is bigger than 1, this could be, for instance, 1 over 3, 1 over 4, then 1 minus this term is always less than 1. And that means that sigma induced is always less than sigma. The charge that's induced in the dielectric material is always less than the charge on the conducting plates, the charge density.